You see them everywhere now, right? Solar panels, wind turbines popping up.
Absolutely. They're called distributed energy resources, or DERs.
And they're really changing the game for our power grids, mostly for the better, bringing green energy.
Definitely. But there is this surprising side effect.
Yeah, this overvoltage thing. It sounds kind of technical, but basically too much voltage.
Exactly. These clean energy sources can sometimes push the voltage levels too high on the local lines. And that's, well, it's a problem for the grid's health.
Okay, so that's what we're diving into today, this overvoltage challenge, especially on those medium voltage systems.
Precisely. We'll unpack why it's tricky to manage and look at a pretty smart new approach.
Right. The big question being, how do we keep the grid stable, keep it safe, while adding more and more of this clean energy? Okay, let's get into it.
So traditionally, utilities have tools, right?
Voltage regulators, VRs. I know they use those to stop voltage getting too low,
Yeah,
like on hot days when everyone's AC is on full blast.
exactly. Preventing undervoltage. But DERs, they push power back onto the grid. It's a whole new ballgame.
And the other fix is like bigger power lines,
Way too expensive. Massive cost.
or just telling the DRs to stop generating power.
Yeah, that's an economic loss, right? You're curtailing clean energy. Not ideal. So the focus comes back to the VRs.
But even the fancier VR controls, the ones meant for power flowing both ways, they still struggle. Why is that?
Well, there are a few key concerns. The big one, maybe concern #1, is when you have substations and DERs feeding power from potentially both sides of a single VR.
Uh-huh. Like it's getting conflicting signals.
Exactly. The local controls can get confused. They start adjusting constantly back and forth, hitting their limits. It's called a tap runaway.
Tap runaway sounds not good. What does that actually do to the grid?
Think chaos. Wild voltage swings, instability. We've seen simulations where it just bounces between the maximum and minimum settings. It's a serious issue.
Okay, wow. And you mentioned other concerns.
Yeah, quickly. There's concern #2. These local VRs, they can't really fix overvoltage that's happening further upstream, closer to the main substation.
So the problem might still be there, nearer the source.
Right. And if the main substation tries to lower its voltage too much to compensate, it could put other connected circuits, other feeders at risk.
Okay, got it. And number 3.
Concern #3 is a bit tricky. Imagine lots of solar panels are generating. The VRs have lowered the voltage settings to manage potential overvoltage.
Right.
And then suddenly a big cloud passes or lots of DERs just disconnect.
The voltage could suddenly plummet.
Precisely. You get a sudden problematic undervoltage because the system was compensating for the opposite problem just moments before.
So it really feels like the standard toolkit is just, it's not quite up to the job with this modern, more complex grid.
That sums it up pretty well. Which brings us to this proposed solution, a supplementary voltage control scheme.
Supplementary, so it works with the existing VRs.
Exactly. It's designed as a minimal investment fix. It doesn't rip out the local controllers. Instead, it gives them, let's say, intelligent guidance, smart directions, and better voltage targets.
Okay, I like the minimal investment part. How does this smart guidance actually stop those problems, like the tap runaway?
Well, first, it's programmed to know which side the main substation feeder is on, always.
So it gives the VR clear, consistent direction, avoiding that push-pull confusion.
Exactly. That directly tackles concern #1, the tap runaway, and then for the other issues.
Yeah.
It monitors voltage at specific pre-identified key locations. We call them critical buses.
So not trying to measure everything everywhere, which would be super expensive.
Right. It's targeted. By watching these critical spots, it can keep the voltage set points optimized to prevent that upstream overvoltage, concern #2, and avoid setting things up for a sudden undervoltage dip if DERs trip off, which was concern #3.
That is clever. Knowing where the substation is, pinpointing critical spots.
Yeah.
And you said it's supplementary. That sounds safer somehow, less risky than a total system change.
Definitely. It's like adding a smart navigation system to your existing car. It enhances capability without replacing the engine. And crucially, if that supplementary system were to fail, for whatever reason,
The original local controls can still operate on their own.
yes, they revert to their standard operation. It provides a layer of reliability, a fallback.
Okay, that makes a lot of sense. And this isn't just theory, right? Has it been tested?
It has, successfully. There were simulations using a standard test system, the IE123 node feeder.
Okay.
And even more compellingly, on data from an actual distribution feeder in Alberta, Canada. This was a real circuit that was experiencing genuine overvoltage issues and even outages because of de-errors.
Did the supplementary scheme help?
Significantly. The study showed it really effectively mitigated the overvoltage problems and prevented those unwanted undervoltage sags.
Wow. So the proof is sort of in the pudding there.
It really seems to be. I mean, the key takeaway here is pretty clear. Integrating all these DEORs effectively, it needs more than just the old playbook.
Yeah, it needs smarter, more adaptable controls that can handle power flowing in multiple directions.
Exactly. Controls that understand this new dynamic grid.
It makes you think, though, as our energy system keeps changing, becoming more decentralized with all this clean power, what other, hidden challenges might be lurking?
That's $1 million question.
And what other smart, lean solutions like this one might be out there waiting? What really stands out to you listening to this, but how our grids are going to have to evolve?